All right, so today we're going to tackle what is honestly one of the greatest scientific achievements in all of history. We are going to decode the story behind the periodic table. And when I say that, I mean the blueprint for, well, for absolutely everything in the entire universe.
Okay, let's just jump right in with a question for you. Think about this for a sec. What do you, your phone, the thing you might be holding in your hand right now, and some distant star, burning billions of miles away, what could they possibly have in common?
Well, the answer is it's the elements. Every single thing you can think of, from the calcium in your bones to the silicon in that computer chip, it's all built from this surprisingly short list of basic, fundamental ingredients.
So let's really dig into that core idea, right? Think of the entire universe as a giant construction set. And the elements, well, they're the building blocks. And this is the magic number. Just 118. That's it. Only 118 known elements. That is the entire toolkit for building planets, stars, and, us. Kind of seems like a small number when you think about all the different stuff that's out there, doesn't it? So what exactly is an element anyway? Well, the most important thing to get is its simplicity. An element is a substance that's as basic as it gets, like the pure copper in a wire, or the helium inside a balloon. You can try to break it down, but you just can't. You can't get anything simpler and still have it be copper or helium. It's kind of like the end of the line.
But, we didn't always know this. Our understanding of elements didn't just appear overnight. Oh no, it was a long journey. A real evolution from ancient mysticism and magic to the hard science of chemistry we know today.
I mean, for thousands of years, the big idea, going all the way back to the ancient Greeks, was that everything was made of just four things: earth, air, fire, and water. But here's the kicker. None of them are actually elements. Earth is a whole bunch of elements mixed together, air is a mix of gases, water is a compound, and fire is a chemical reaction. The real story is just way more fascinating. And you can really see that transition happening right here. On the left, that's the world of the alchemists, part science, part magic, always trying to turn lead into gold. Now, they never pulled that off, but their experiments, they accidentally laid the groundwork for the real chemists, like John Dalton, over on the right. See how he's starting to think about elements as these unique little particles? He's organizing things, thinking about matter in a whole new, systematic way. It's a game changer. And this timeline really shows how one discovery just led to the next, like dominoes falling. It starts in the 1660s with Robert Boyle, who starts applying this scientific method to this stuff. Then, 100 years later, bam, Lavoisier proves water is actually a compound. That discovery leads directly to Dalton's atomic theory, this idea that every element is made of its own unique particle. And once you have that idea, well, then you can use new tools, like electricity, which is what Humphrey Davy did to find a whole bunch of new elements. It was a total scientific revolution. Okay, so this all leads to the big question, right? What are these unique particles that Dalton was talking about? To figure that out, we have to go small. I mean, really small. We've got to decode the atom itself. And here they are, the three tiny particles that build every single element. You've got your positive protons and neutral neutrons packed tightly together in the middle, that's the nucleus, and then you have these negative electrons zipping around the outside. That's it. Just three simple parts, but how they're arranged, well, that's everything. And this right here, this brings us to what might be the single most important number in all of chemistry, the atomic number. It's super simple. It's just the number of protons in an atom's nucleus. Think of it like a unique ID badge for every element. It's what makes an element what it is. If you change the number of protons, you literally change the element. Period. Just look at how this works in practice. So, you've got hydrogen up there with just one proton. Its atomic number is 1. Simple enough. But if you add 2 more protons to the mix, you don't just have a bigger hydrogen atom. Nope, you get a totally different element. Lithium, atomic number 3. Same building blocks, completely different results. Okay, so let's set the scene. By the mid-1800s, scientists have found dozens of these elements. But it's a mess. It's just a chaotic list of ingredients with no rhyme or reason. What they desperately needed was a system, some kind of organizational masterpiece. And this is the man for the job. Enter Dmitry Mendeleev. In 1869, this brilliant Russian chemist has a massive breakthrough. he starts noticing that the properties of the elements, they repeat, not randomly, but in a predictable periodic pattern. But this is what made him an absolute genius. It's not just what he knew, it's what he didn't know. He didn't just organize the elements they already had. He was so confident in his pattern that he left gaps, empty spaces, in his table for elements that hadn't even been discovered yet. And he didn't just leave a blank spot. He predicted their properties, like how much they'd weigh, what their density would be. That is just so bold. And guess what? When those elements were finally found years later, he was right. His predictions were spot on. And that's what turned his little chart from a neat idea into a powerful predictive scientific theory.
So how does this incredible map actually work? Well, it's organized in two main ways. When you read across the rows, those are called periods, you're basically adding layers of electrons to the atoms. But the real magic, the really useful part, is in the columns, which we call groups. Everything in the same column behaves in a really similar way. They're basically like little chemical families.
And here it is, the final results, an elegant, logical, and just incredibly powerful grid. The periodic table isn't just a poster you see in a science class. It's more than a list. It's a map. It is the ultimate cheat sheet for the building blocks of matter. So, okay, we have our amazing, organized list. Now let's zoom back out from the tiny atoms and see these elements in action. I mean, how do they actually combine and react with each other to create the world we all see and live in? And honestly, there's no better place to start than by looking at, ourselves, you. Believe it or not, about 99% of your entire body is made from just 6 elements. That's it, 6, just combined in all sorts of complex ways. You are, quite literally, a walking, talking collection of chemical compounds. And as you can see, oxygen is the big one, making up most of you. Now, some of these combinations, these chemical reactions, can happen incredibly fast. Here's a great example. We're looking at a piece of pure lithium metal. When you heat it up, it starts reacting with the oxygen in the air and boom, it ignites, releasing a ton of energy as heat and light and forming a completely new substance in the process. But of course, not all reactions are that explosive and dramatic. On the complete other end of the spectrum, you have something like this. This old ship shows us a much slower and probably more familiar chemical reaction. Over years and years, the iron in the ship's hull has been slowly reacting with oxygen to form iron oxide, which of course we all just call rust. It's the same basic principle as the lithium reaction, just playing out over a much, much longer time.
So there you have it. We've gone from the chaos of ancient alchemy all the way to the beautiful, perfect order of the periodic table. We've mapped out the 118 fundamental ingredients that build our entire reality. We basically have the universe's parts list. And so that leaves us with one final, huge question. Now that we know what everything is made of, what are we going to build with it next?